Tenneco optimized the design of the second-generation NTE shock absorber developed by KPI. The valve housing was optimized and the material was changed from steel to aluminum. Rivets were used to close the drillings in the valve blocks, and the end loop was changed to fit the bushing of the Hyundai Kona's rear suspension. Parts for 3 prototypes were manufactured. Three prototypes were assembled. A dedicated filling port was added to the damper. This enabled the use of a professional vacuum filling machine to fill the damper with oil, minimizing air content. This reduces hysteresis and improves damping performance. A hand pump was then used to increase the static pressure to 1 bar relative. This further reduces hysteresis and cavitation and improves the response time of the damper. The safety valves and throttles were tuned to reach a maximum pressure of 280 bar in both the rebound and compression chambers. This level is sufficient for intrusion while remaining low enough to avoid damaging components. A dynamometer was used to actuate the shock absorber by applying the required displacement and velocity. In Test A, a sinusoidal input is used in which the displacement amplitude remains constant while the velocity increases. Each cycle is applied 3 times to verify the repeatability of the measurements. Signals are logged by the dynamometer and an external logger. The dynamometer records shock absorber displacement and force, and the external logger records compression and rebound pressures, as well as the voltages generated by the NTE capsules. The data is then used to construct the force displacement and force velocity diagrams of the shock absorber. The results indicate fast force buildup and limited hysteresis, indicative of good oil filling and proper tuning. The measured pressures are also evaluated and show to be in the desired range. Furthermore, the voltages generated by the NTE capsules were recorded at various resistance values for further analysis. These signals allow a comprehensive evaluation of the shock absorber's performance. In Test B, a sinusoidal input is applied wherein the frequency is increased, but the velocity is kept constant. Each sinusoidal input profile is again applied for 3 full periods to assess repeatability. Like before, the force displacement and force velocity diagrams of the shock absorber are constructed, providing insight how frequency affects damping performance. The pressure and voltage behaviors were also again recorded and analyzed. In addition to tests A and B, a standardized curving program was also ran on the dynamometer to characterize the damping according to Tenneco's in-house developed procedures. This test results in the force displacement, force velocity, and general damping characteristics of the damper. A portable dynamometer was designed and built that allows to demonstrate the functionality of the damper off-site.